Hello! Today, in preparation for talking about audio circuits, I'm going to talk about the nature of sound. So first let's talk about what waves are, because sounds are waves. So there are two phenomena that are related but different that we call waves. Sound waves are a type of energy wave. So let's take a quick look at what that is and what they do. So if we have a pond, it's a windless morning, there have been no recent earthquakes or anything like that, so that pond is going to be perfectly flat. So now let's just drop a rock in there. So let's drop a rock in. What's that going to do? It's going to drag some water down with it. So there is our rock hitting the water, dragging some water down with it. Well, that is going to push water off to the side, because as the rock hits it, it's going to push water out of the way. Well, water is virtually incompressible, so it can't actually create this shape I've made here, because that would mean that some of the water has to become compressed in this area. So what's going to happen is that's going to push that water up and create a couple of, we'll call them waves. So technically I would think they would be pulses, but we'll call them waves. So the water has to push up because it can't compress. And so now we have these two humps and a valley in the middle where the rock has pulled the water down. And also this has imparted some energy in that direction. So what's going to happen is this wave is going to push energy in this direction, causing the water next to it to also push up. And then same thing's going to happen over here. But at the same time, gravity is pulling this wave downwards, and so it's going to fall. So what happens is that we end up with the energy going away, and I'll just go ahead and show that as a fallen area there. And so as that falls, the energy pushes away and the water next to it pushes upwards. And of course, this is a very smooth action. We don't see it as I'm drawing it here. And of course, what happens here is our rock eventually falls down. There's nothing holding this water down. There's hydrostatic pressure pushing on it, wanting to push it back up, so that water in the middle is going to push up again. So now we have a bump where there was a valley. Gravity wants to pull this down. Next to it are two valleys. Hydrostatic pressure wants to push them up. And then we have the same thing over here where water is pushed up and gravity wants to push it down, plus it has energy pushing that way. And so that's going to cause water next to it to do exactly the same thing. This is going to go up. It's going to go up. This wants to come down because gravity is pulling it down. Hydrostatic pressure is pushing that up. And so what we get is a very smooth wave, and I'll show, of course you've seen them before, but that's what a wave looks like. We get this energy going down. And so why we call it an energy wave is because at this point right here, we have the water above the equilibrium level. So gravity is pulling down on it more than hydrostatic pressure is pushing up. And so we have potential energy. Potential energy is the potential to produce kinetic energy. So if I hold this pin about 5 feet, about 2 meters above the ground, it has the potential to fall and therefore create kinetic energy, the energy of motion. But it doesn't have that kinetic energy because I'm holding it, so it only has the potential to create the kinetic energy. But if I drop it, then it falls, and while it's falling, it has kinetic energy. And when it hits the floor, it imparts that kinetic energy into the floor, and it is dissipated in different ways as heat and sound waves as it hits the floor. So potential energy when I'm holding it, kinetic energy when it's moving. And we have the same thing here in this energy wave. Right now this has potential energy, but as gravity pulls it down, it has kinetic energy. And then later on, when that gets to the bottom, it has potential energy again, with hydrostatic pressure wanting to push it up to create kinetic energy. So we continually have the wave trading off between kinetic energy, kinetic energy, and potential energy. When it's moving, it's kinetic energy. When it's in a state where it's ready to move, it has potential energy. And then that wave energy dissipates outwards, and as it goes out, it spreads into more and more water, so it gets more and more shallow and eventually completely dissipates as the energy dissipates out into the water, or what little heat it creates dissipates into the air, and eventually our pond will smooth out again. So that is a energy wave. But the other thing we call waves are something that we cannot see, but it's something that most often we see in electronic circuits, where we have something like voltage, and let's have a scale where we have time on the horizontal scale and voltage on the vertical scale. So at this time we have that voltage. The voltage goes up as time changes, and as time goes by the voltage goes down and back up and back down and back up. So we don't have quite the same thing, but looks very similar to a wave. So what do we call it? We call it a wave. So what it really is just a voltage that's going up and down and up and down. It's changing that way. It could be a current going up and down. There are other things that could change, but usually this kind of wave is a voltage wave. And so it's just simply a voltage that's changing over time. Voltage goes up, voltage goes down, voltage goes up, voltage goes down periodically, so that maybe this happens every second or every tenth of a second, or in very high frequencies it might be every microsecond or nanosecond, but it happens periodically. And we also call that a wave because we put this on an oscilloscope, which is a voltmeter that shows us voltage over time, and it looks like a wave. So with audio circuits, what we're going to be working with is turning sound waves into this other kind of wave. Let's talk about sound waves real quickly. We talked about like waves on a pond, but sound waves are a little different. They're compression waves. And so here is an illustration of a expanding and contracting ball, and as it expands, it pushes air molecules together and creates higher pressure. But under the higher pressure, they want to push apart, and so we have potential energy trying to push them apart. As they go apart, we have kinetic energy. And like the energy wave I showed before, momentum is going to cause them to go through the equilibrium level. I didn't mention that before, but what causes it to go through the equilibrium and keep going is momentum. Sound waves have the same thing. They compress. As they decompress, it creates momentum, so it rarefies. Now the air pressure wants to push it back together, and we get the waves going in and out. And of course, they spread out just like the energy waves on a pond. And so here is a sphere that is creating pressure waves, which are what sound waves are. So it's changes in pressure in the air. When it comes to sound, that is something that we hear. So those sounds hit our eardrums and cause them to vibrate. As it rarefies, it pulls our eardrum out. As it pressure rises, it pushes our eardrum in, and as that eardrum vibrates, we have an inner ear system of liquids and little tiny hairs that are connected to nerves that can detect certain frequencies, and those are eventually processed by our brain, and we hear those as sound. I mentioned frequencies, so let's quickly say what that is. In the illustration I just had with the waves going up and down with time going that way and voltage that way. Well, let's say we had a peak every second. That voltage is changing up and down once every second. So we hit our peak, which is, let's say that's positive 1 volt, and let's say the other peak is negative 1 volt. And so it reaches the positive 1 volt once every second. Well, that would be a frequency of 1 cycle per second. If that happens every half second, that would be 2 cycles per second, and we call a cycle per second 1 hertz. So 2 cycles per second would be 2 hertz. 1,000 cycles per second would be 1,000 hertz, or 1 kilohertz. So that is what frequency is. And when it comes to sound, we perceive frequency as pitch. So lower frequencies we hear as a low pitch, and higher frequencies we hear as a higher pitch. The lowest frequency we can technically hear is 20 hertz, or 20 cycles per second. Now, we can actually hear lower frequencies when we talk about what is a threshold of something. It's usually a point where its power is 1/2 of the peak power. So at 20 hertz, our ears are half as sensitive as they are to the peak sensitivity, which is somewhere around 1,000 hertz. So our halfway point is 20 hertz, so we call that our lower limit. But we can also hear sounds all the way up to 20,000 hertz, or 20 kilohertz. That should be a lowercase k, so I will be correct and make that lowercase. So our hearing range is from 20 cycles per second to 20,000 cycles per second. Of course, we can hear frequencies slightly higher than that because the 20 kilohertz would be the point where our ears are half as sensitive as they are to the peak, which is once again around 1,000 hertz. Other aspects we want to know about waves would be wavelength. That only pertains to physical waves, actual energy waves. The wavelength is the distance between the peaks. So we have our waves on the pond again, and those waves are moving whatever direction they're moving. And the wavelength would be the distance between these two peaks as they travel along. And in sound waves, that would be the difference between the high pressure peaks. So we have a high pressure area here, low pressure, high pressure, and those are moving through the air. And the distance between those high pressure peaks or the low pressure valleys, you just pick any 2 points. So we could use the peaks, we could use the valleys. They're the same distance. That's the wavelength represented by the Greek letter lambda. So in a ocean wave, these might be 10 feet apart or 3 meters apart. And in sound waves, they might be anywhere from, I have to do the calculations, I'll put it up here. At 20 hertz, they would be, I think, about 3 meters apart. Don't quote me, I'll put it up here. And at 20 kilohertz, they're going to be much, much closer together because if the sound is moving at a constant speed, but we're making the peaks more often, peaks will be closer together. So wavelength of a low pitch is going to be very long. Wavelength of a high pitch is going to be very short. And when it comes to radio waves that we will talk about in the communications portion of the class, we have the same thing where I do know that 1 megahertz waves are 300 meters between peaks. That would be peaks of our magnetic and electric fields. But back to sound waves, we would have our peaks of pressure somewhere around 3 meters, I think, for 20 hertz, and whatever it is I'll put up here for 20 kilohertz. They get very close together. So that's the wavelength. Another thing we want to talk about is amplitude, and that is how high the peaks are. So a physical wave, how high are those peaks compared to the valleys? Well, there's different ways to measure amplitude. We could measure from the mean to the peak. So from there to there, or from there to there, mean to peak or mean to valley, or peak to valley, which we would actually call peak to peak. And there's another one we use in electronics called RMS, and that's kind of an average, not really, but RMS is a measure of, we take a measurement, many measurements along the wave, we take the square root of those, average them together, then square them, and then we end up with a number that's kind of an average, but it's not really an average. It's actually a level that contains the same amount of energy as the wave. In our electric wave, where it's voltage, here's a voltage that's constantly changing. Well, there is a steady DC voltage that contains the same energy, and that would be the RMS. And once again, we can calculate that by measuring a bunch of points of the wave, taking the square root, averaging that, and then squaring that, and we would get the RMS, root mean square. That gives us a DC voltage that is equal to the energy of this alternating voltage or alternating current. So that would be the amplitude. Amplitude is measured, once again, either from the mean, that's the RMS there, so let's put the mean down here, the normal right there. So we measure from the mean to a peak, that's the peak voltage, the peak to the valley, or the peak to peak, that's the peak to peak measurement. And then in electronics, we have the RMS, which is the DC voltage that contains the same energy. When it comes to sound, we have sound pressure to deal with, because what is sound? It's waves that are varying pressure in the air. So how much is that pressure? Well, that's we actually take an RMS version of that, so we can use RMS for air pressure. I'm not going to get into a lot of detail about that, but we have sound pressure hitting our ears. High pressure, low pressure, high pressure, low pressure causes our eardrums to vibrate. The lowest sound pressure that we can detect is 20 micropascals. So Pascal, I forgot off the top of my head what that is, but that's not a lot of pressure. I'll put it up here, the definition of a Pascal. But that has to do with how much pressure per unit area we have. 21 millionths of a Pascal RMS vibrating our eardrum, we can detect that. I'm a little oversimplifying, but that's the lowest pressure we can technically hear. If we increase that about 1 trillion times, we would actually start to feel pain, the threshold of pain. So when we measure sound pressure levels, we use what's called decibels. And particularly we call that sound pressure level decibels. If we change the properties of this to compensate for the fact that our hearing is not linear, in other words, we don't have the same sensitivity to some frequencies as others, we get something called dBA. But I'm not going to get into the engineering too much. I just want to give a quick overview. So the main thing we talk about when we measure sound is decibels, sound pressure level. What's a decibel? You can see my video on the quick look at decibels, but basically we're talking about ratios. So a sound pressure level of 3 decibels, SPL, which means we're referencing to this. So what are we talking about? Once again, decibels are a ratio. So we have a reference point. So we have our reference point of 20 micropascals. If we double that to 40 micropascals, that equals positive 3 decibels of our sound level. So if we double it, we get 3 decibels. If we cut it in half, we get minus 3 decibels. So if we go above 20 micropascals, we have positive decibels. If we double that, it's 3 decibels. If we double it again, it's 6 decibels. So every time we double it, we add 3 decibels. If we multiply it by 10, how convenient. We get 10 decibels. But if we multiply it by 100, we get 20 decibels. It's a logarithmic scale. So what you need to remember about decibels, just very, very, very quickly, so we don't get too confused, a 2-to-1 ratio equals 3 decibels. A 10-to-1 ratio equals 10 decibels. 100-to-1 equals 20 decibels. 1,000-to-1 equals 30 decibels. So being logarithmic, we get these increasingly bigger and bigger ratios, stay fairly small numbers. So we get up to our threshold of pain, which is 120 decibels. Can you see the pattern here? Let's see. We have a 1 in the 10, that's 1 0. A 2 in the 20, that's 2 zeros. A 3 in the 30, that's 3 zeros. Well, that's one way to help remember it. So 30 decibels, 3 in the 30, we get 3 zeros. So this means we have how many zeros? 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to 1 equals 120 decibels. And so it's a, what do we have here? Million, billion, trillion. So we have about a 1,000,000,000,000-to-1 ratio. So our sound pressure level is about 1 trillion times our 20 micropascals. Easier to write trillion than to write all those zeros. 1 trillion times 20 micropascals comes out to be 120 dB. So that's how we measure sound in dB. It's a ratio compared to 20 micropascals. So if we go below that level, it's going to be negative decibels, but we never talk about negative decibels because we can't hear them. So that's what we're talking about with decibels. So we just remember, 2-to-1 is 3 decibels, 10-to-1 is 10 decibels, 100-to-1 is 20, 1,000-to-1 is 30. Remember, the first digit in this number will tell you how many zeros are there, so we can see what that ratio is. So that's what decibels are. And when we talk about sound decibels, we use decibels to measure lots of things besides sound. But in sound decibels, it's typically going to be decibels SPL, which means we are measuring how much higher we are above 20 micropascals. So 0 decibels is a ratio of 1-to-1 to 20 micropascals. So that's going to be 0 dB. What's the next one up? We double that to 40 micropascals, and that's going to be 3 decibels. We double that again to 80 micropascals, that's going to be 6 decibels. So every time we double it, we go up 3 decibels. Every time we multiply it by 10, we go up 10 decibels. So as I showed you before. So that's what we're talking about when we talk about sound decibels. Okay, what's the other things we can measure about sound? Speed of sound. Speed of sound we usually think of as, here in America we use miles per hour. So at 20 degrees C at sea level, the speed of sound is about 767 miles per hour. But of course, for the rest of the civilized world, that would be, I have to convert this because I think in miles per hour, that's going to be 1,231 kilometers per hour or 342 meters per second in air at sea level at 20 degrees Celsius. Now, in other mediums, sound travels faster. Sound travels much faster in water. In water, it's fresh water, it's going to go at 20 degrees C, fresh water at surface level pressure. It's going to move at approximately 1,482 meters per second. And in steel, sound travels at 14,900 meters per second or about 33,000 miles per hour. So sound travels much faster through steel, a little slower through water. Through air, it doesn't go nearly as fast as through other mediums. And that's why earthquake waves travel at thousands of miles per hour through the earth, because what's an earthquake wave? That wave that causes the shaking travels through the earth at thousands of miles per hour because it's a sound wave traveling through rock. And it travels through rock a lot faster than it does air. So speed of sound through air is typically about 767 miles per hour or 342 meters per second at sea level at 20 degrees Celsius. At higher levels, it slows down because the air gets more rarefied, so the sound cannot move as fast. So higher temperatures, which means the air is more rarefied, or higher altitude, sound actually moves slower. And finally, sound does have a direction. It's going to be moving some direction through the air, and we can also detect what direction it's coming from. And we can use different types of microphones or reflectors or whatever to tell which direction sound is coming from, because we can focus it just like we can focus light waves with a lens. So just real quickly, I'll talk about this more when we talk about microphones, but just as a lens, which is a piece of glass with curved surfaces, can cause light to bend. So the light at the edges bends to there, the light there bends. So because of the curve, the bend is different at different parts and ends up with the lights, all the light focusing at one point. And we can do that with a mirror too. A curved mirror, light comes in and from the edge comes there, from that edge comes there. If the mirror is a shape called a parabola, then they will all the light that comes in parallel to the axis will focus in one place. Not going to get into more details about that, but we can focus light with a curved mirror. Or if that's sound, we can have a curved reflecting surface, such as a parabolic reflector. You've seen them, especially if you've ever watched a football game. There's always some guy with a little parabolic reflector trying to get the sound of the quarterback. Put a microphone right here, and the sound coming directly in is going to end up right there. But if it's coming in at an angle, it's going to end up somewhere else. So it misses the microphone. So we can actually tell which direction the sound is coming from with a parabolic reflector or other types of microphones we'll talk about down the road. So those are the basic characteristics of sound we need to know about. So what were they? They were frequency, which is how often the sound peaks, how many times per second. We call that the frequency. The wavelength is how far apart those peaks are in the air because it's traveling through air. The higher frequency, the peaks will be closer together. Lower frequency, they will be further apart. And the other thing we want to know about is amplitude. How powerful is it? So and amplitude can be measured either the peak to the mean or peak to valley. There are two different measurements, although one's double of the other. Or RMS, which is a steady pressure that has the same power as that changing pressure of your typical sound. And RMS is used basically for calculations in sound. And in electronics, we talk about that back in the AC class because we have RMS volts too that we use in alternating current. Sound pressure, that's what we hear. How much pressure hits our eardrum causes it to vibrate, and we can detect pressures of as low as 20 micropascals. And if we multiply that by 1 trillion, we would actually feel pain. And we measure these large ranges in a measurement called decibels because that takes huge, huge numbers and squeezes them into small numbers. So the threshold of hearing would be 0 decibels, and the threshold of pain is 120 decibels. And remember that first digits before the 0 in decibels, if we have 120 decibels, that's a 12 before the 0, so that would be a 1 with 12 zeros after it. So that's a trillion. So what's 120 decibels? That's a trillion times 20 micropascals. The speed of sound through air at sea level and 20 degrees C is 767 miles per hour and 1,231 kilometers per hour, or 342 meters per second. And just as I mentioned, the study of sound is called acoustics. So if you are working with acoustics, working with noise control or sound control or sound systems, you would be an acoustical engineer. And you might be called an acoustical technician if you work with sound systems, but you would be more likely called a sound technician. Noise, another thing we need to deal with. Noise is unwanted sound. So if you have sound that you want to pick up, like a conversation in a noisy room, well, the sound you don't want is the noise. In an electrical system, noise is any signal other than the one you want to pick up. So in electrical systems, you might have noise, such as transistors create what's called quantum noise. Because of random movement of electrons, you get a little bit of a hissing sound. Well, that's unwanted, so we call that noise. You also might get noise from electromagnetic waves hitting your system and causing either spikes, such as the lightning strike will cause spikes of noise. 60 hertz or 50 hertz radiation coming from our wiring might be picked up. We call that noise. Anything that's not what we want to pick up, we call noise. And we have what's called the signal-to-noise ratio. We want a high signal-to-noise ratio. We want our signal that we want a lot higher than our noise. If our signal-to-noise ratio is low, we're going to have trouble with the noise in the system. So that's what noise is anything that's unwanted. In sound, we call noise sounds we don't want. In electricity, any other signal we don't want is called noise. And when we convert sound to electrical signals, we have to deal with both. We have noise in the acoustic sound before it gets to the microphone. And once it gets to the electronic system, we have electrical noise to deal with. And that's basically what we need to know about sound before we start talking about audio circuits. So the next thing we'll talk about is converting sound waves into electrical waves that we can deal with in electronic circuits. So our next video will be about a type of transducer. A transducer is something that converts one type of energy to another. And sometimes you will hear people talk about transducers, and what they mean is microphones. And so microphones are a specific type of transducer, and that's what we will be talking about next, is microphones, which convert sound waves into electrical waves that we can deal with electrical circuits. So I hope you found this useful and informative. If you did, please give me a thumbs up. It really helps the channel and helps other people find these videos. And to help me keep making these videos and to keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. And if you want to study electronics technology and perhaps become a certified electronics technician, or just get a jump start in your studies in electrical engineering, you can go to Vocademy.net and take my free course. And a big thank you to my patrons at Patreon and my one-time donors. I could not do this without your support. So another big thank you. I wish I had the time to thank you individually, but I do as often as I can. And a big thanks to everyone for watching. Hope I can edit that into something coherent.